Imagine a simple paper clip. You bend it once, it's fine. Bend it back and forth again and again. Eventually it snaps. This, in essence, is fatigue. It's a phenomenon that affects almost everything we build, from colossal bridges to the tiniest components in your mobile phone. Strain life fatigue analysis, often called the εN method, is our rather clever way of understanding and predicting this. It helps us design things that last, things that are safe. It's a vital tool for any engineer wanting to ensure their creations can withstand the rigors of repeated use, the countless cycles of push and pull over their intended lifespan. Without it, we'd be navigating a universe of potential failures, largely in the dark. Why is this so important, you ask? Well, unexpected failures can be catastrophic. Think of an aircraft component failing mid-flight, or a critical part in a medical implant giving way. The consequences can be dire, both in terms of safety and economic cost. Strain life analysis allows us to peer into the future life of a component. It considers how a material responds not just to a single large force, but to countless smaller, repeated loads. These loads might individually seem insignificant, well below the material's ultimate strength. Yet, under repetition, they initiate tiny cracks which then grow stealthily until the component can no longer bear the load. It's a silent process, this fatigue. The εN method specifically focuses on strain. Strain is a measure of deformation, how much a material stretches or compresses under load. This is particularly crucial in areas where stresses concentrate, perhaps at a notch, a hole, or a sharp corner in a design. These are the places where fatigue cracks love to start their insidious journey. Traditional methods might look at overall stress, but strain life delves into the local strain conditions. It acknowledges that even if the bulk of a structure is under low stress, these tiny localized regions can be experiencing much higher strains, especially when plastic deformation, a permanent change in shape, occurs. This detailed view is what makes the method so powerful. Ultimately, understanding fatigue through strain life analysis is about building a more reliable world. It's about preventing those sudden, unwelcome surprises. It allows engineers to make informed decisions, to choose the right materials, and to optimize designs. This ensures that structures and products perform as expected, safely and efficiently throughout their service life. From the grandest engineering marvels to everyday objects, the principles of fatigue are always at play. Knowing how to analyze them helps us build better, stronger, and more durable things, preventing a cascade of problems before they even begin, which is rather a good thing for everyone. Materials at an atomic level are a vibrant dance of atoms held together by electromagnetic forces. When we apply a load, we're essentially stretching or compressing these bonds. If the load is small, the atoms return to their original positions once it's removed. This is elastic deformation, but apply a larger load or apply smaller loads repeatedly and things can change. The atoms can be permanently displaced. This is plastic deformation. Fatigue failure is a consequence of this repeated microscopic dance, where cyclic loading causes irreversible damage. This damage accumulates cycle by cycle, like tiny ripples growing into a wave, eventually leading to a crack and then ultimately to failure. It's a gradual weakening process. The εN method is unique because it directly correlates strain, the actual deformation experienced by the material locally, with the number of cycles it can endure before failing. It doesn't just look at the force applied, it looks at how the material responds to that force. This is especially important for low-cycle fatigue. This is where a component might fail after a relatively small number of quite large strain cycles, often involving significant plastic deformation. Think about the landing gear of an aircraft. It experiences high loads, but not millions of times a day. The strain life approach captures this behavior with remarkable accuracy by considering both the elastic and plastic components of strain from the very start. This brings us to a rather elegant piece of engineering insight, the Coffin-Manson-Basquin relationship. It sounds complicated, but it's a beautiful equation that helps us quantify this fatigue life. It essentially states that the total strain amplitude, epsilon sub A, a material experiences is related to the number of reversals to failure, to n sub f, where n sub f is cycles. This total strain is made up of two parts, an elastic part and a plastic part. The Basquin part of the equation describes the elastic strain component, dominant in high cycle fatigue. The Coffin-Manson part describes the plastic strain component, which is critical for understanding low cycle fatigue, where those larger, permanent deformations occur. So what does this relationship tell us? It provides a curve, specific to each material, plotting strain amplitude against the number of cycles to failure. Engineers conduct tests on material samples, cycling them at different strain levels until they fail. These data points create the epsilon n curve. This curve then becomes a powerful predictive tool. If we know the cyclic strain a component will experience in a particular spot, we can use this curve to estimate how many cycles it will last. It's a cornerstone of modern fatigue design, allowing us to understand the limits of our materials with much greater clarity and confidence than before. Engineers have a couple of main tools in their toolkit for predicting fatigue life. The older, more traditional method is the stress life approach, often called the SN method. Here, the focus is on the nominal stress amplitude, S, applied to a component versus the number of cycles to failure, N. This method works quite well for high cycle fatigue situations. Think of millions or even billions of relatively small stress cycles. In these cases, the material behavior is predominantly elastic. There's very little, if any, plastic deformation occurring at the critical locations. It's simpler, often requiring less detailed input. The strain life, or epsilon n method, however, takes a different, more detailed perspective. It shines when dealing with low cycle fatigue. This is where plastic deformation, that permanent set in the material, becomes significant. Stress concentrations like notches or holes cause local yielding even if the overall applied load is not enormous. The SN method struggles here because stress is no longer simply proportional to strain once you enter the plastic region. The epsilon n method, by directly considering strain, provides a much more accurate picture in these complex scenarios. It's like using a microscope instead of a magnifying glass for the really fine details of material response. So when do we use which? The SN approach is often suitable for components like rotating shafts or springs that experience many cycles under relatively low, primarily elastic stresses. Its limitations appear when local stresses exceed the material's yield strength, leading to plasticity. For pressure vessels, the regions around nozzles or openings can experience high local strains during pressure cycles. Here, the epsilon n method is far superior. Aerospace components such as fuselage cutouts or landing gear parts often involve complex geometries and load histories where local yielding is a key concern. The epsilon n approach is indispensable for ensuring their integrity under demanding operational conditions. In the automotive world, many components are prime candidates for strain life analysis. Consider engine connecting rods, crankshafts, or suspension parts. These experience significant cyclic loads, often with stress concentrations that lead to local plastic deformation. Using the epsilon n method allows designers to optimize these parts for durability, reducing weight, while ensuring they can withstand the harsh conditions of daily driving or even extreme performance. It's about understanding that local microscopic yielding, which the SN curve might miss, but which the epsilon n method captures, providing a more robust and reliable design prediction for these critical applications. To truly harness the power of strain life analysis, we need to accurately determine those local strains. This is where non-linear finite element analysis becomes incredibly valuable. FEA allows us to create a virtual model of a component. We can then apply simulated loads and see how the material deforms point by point. Nonlinear FEA is crucial because it can account for material plasticity, that permanent deformation we've talked about. It can also handle large deflections and contact between parts. This gives us a very precise map of the strain distribution, especially in those critical high-strain areas, which is essential input for an accurate epsilon n fatigue calculation. Another vital consideration is the presence of mean stresses. Most real-world components don't just cycle around zero stress or strain. They often have a steady or mean tensile or compressive stress upon which the cyclic load is superimposed. A tensile mean stress, for instance, generally makes fatigue life shorter. It's like pulling a rope taut before you start wiggling it. It's more likely to snap. Clever engineers have developed mean stress correction models, such as the Morrow or Smith-Watson-Topper SWT methods. These adjust the baseline epsilon n curve to account for these mean stress effects, leading to much more realistic life predictions for components under real-world service conditions. Furthermore, components rarely experience simple, constant amplitude, cyclic loading. Think of a car suspension. It sees a complex, variable history of bumps and loads depending on the road surface and driving style. Using a simplified, constant amplitude cycle in our analysis might be misleading. Therefore, employing real-world load histories, often gathered through data acquisition on prototypes or existing products, is paramount. This rainflow counting of complex histories into equivalent cycles allows the epsilon n method to provide a far more accurate prediction of life under the actual conditions the component will face. It's about bringing the messy reality of the world into our precise calculations. This is where Product Development Engineers Ltd truly excels. We possess deep expertise in applying strain-life fatigue analysis, integrating advanced nonlinear FEA, appropriate mean stress corrections, and realistic load histories. We understand the nuances that turn a good analysis into a great one, ensuring your products are robust and reliable. Crucially, we are passionate about supporting clients in low and middle-income countries and emerging economies. We believe that access to world-class engineering expertise can drive innovation and growth everywhere. Product Development Engineers Ltd offers not just solutions, but a partnership dedicated to engineering a stronger, more resilient future together.